Hi everybody, welcome to our next lecture on rotational mechanics. We're going to look at three different things, something called moment of inertia, rotational kinetic energy, in other words, how energy is affected when something rotates, and the idea of angular momentum, again, sort of rotational momentum. Um, there's an interesting thing. We talked about the idea of inertia, and one of the ways we described inertia was an object's resistance to changes in motion. Okay? So when something rotates, it also will have a certain resistance to any change in that rotational motion. And so this is where the idea of the moment of inertia, which occurs in rotational mechanics. So the moment of inertia of an object would be described as its resistance to rotation, how much it will actually resist rotating, particularly when torques are applied. And one of the things that tends to affect an object's moment of inertia is its mass and its shape. So let's look at that in terms of two different rotating objects, a solid disk and a thin hoop. And we'll look at that on a simulation. Okay, so here what I have is a solid disk. Okay, it has a mass of 0.1 kilograms and a radius of about 4 meters. And we're going to apply a continuous 5 Newton torque to it. Okay, so when we do that, we notice that this has a specific moment of inertia of around 0.8 kilogram meter squared. And the platform will accelerate at 6.25 radians per second squared. Okay, it has an angular acceleration because it's rotating. Now, if I were to double the mass, notice doubling the mass doubled that moment of inertia, okay, increased its resistance to rotation. And the immediate effect was that the angular acceleration was cut in half. Okay, because there is a greater resistance to rotation, it will not accelerate as much. And the ladybug just went flying off. Let's return that mass back to what it was. Okay, so now we're back down to our original acceleration and moment of inertia. Now instead, let's cut my radius in half. Notice that by cutting the radius in half, my moment of inertia decreased by 1/4. So radius clearly has a much larger effect. In fact, it has a squared effect on resistance to rotation. So by reducing the radius by half, the moment of inertia decreased by 1/4, making it much less resistant to rotation. And that caused an increase in the angular acceleration of 4 times. So again, smaller resistance to rotation, greater acceleration of the object. Now, back to my original situation with my solid disk. I'm going to change it from a disk to a thin hoop. So that means instead of a solid disk, it looks like this, a very thin hoop. Now, what you'll notice that by changing the shape, okay, so I didn't change the mass or the radius, I just changed the shape of it from a disk to a hoop. By going from a disk to a hoop, my moment of inertia went up. So a hoop actually resists rotating more than a solid disk. It's almost the opposite of what you might think. So that shape has an effect. By changing it to a hoop from a disk, I actually doubled my moment of inertia. And that had the same effect before of changing something. Once I doubled my moment of inertia, it cut my angular acceleration in half. Okay? So clearly, what affects an object's resistance to rotation, how easily or how difficult it is to rotate an object, is based on its mass and its shape or radius, or what type of object it is you're rotating. Now, then that sort of segues into the idea of a rotational kinetic energy. Now, we've already defined kinetic energy, energy due to motion. Anything in motion has kinetic energy. But it turns out there's actually two sort of subcategories of kinetic energy. Really, anything that is sliding is said to have something called translational kinetic energy. Okay? Now, to translate sort of just means just to move forward. But a rolling object, because it's moving forward, has translational kinetic energy also, but also has an additional component called rotational kinetic energy. So what that means, again, anything that is simply has mass and is sliding with a certain velocity has this translational kinetic energy, that 1/2 mv squared. But something with mass that is rolling, okay? Now, if it's rolling, of course, it has a linear velocity because it's moving forward, but it also has an angular velocity because it's rotating. So that's two types of velocities. And so it has translational kinetic energy because it is moving forward with a linear velocity, but it also has rotational kinetic energy because it has that angular velocity. Okay? Now there's actually a way of calculating rotational kinetic energy. It's given by this equation 1/2 I is the symbol for moment of inertia, and omega squared, angular velocity squared. I'm not going to really get into any equations with it today, but that's one of the reasons why a wheel is such a great way to move something, because by having a wheel moving, you get more kinetic energy than if something is simply just sliding. Now, of course, if something can have rotational kinetic energy, it can also have rotational momentum. Okay, remember again, momentum is the idea of mass and velocity. So an object that spins with an angular velocity has a type of momentum called angular momentum. Okay? Not linear momentum, but angular momentum, although there are some similarities between the two. So your angular momentum is actually the product of your moment of inertia and your angular velocity. That's how it's done. Linear momentum was mass times linear velocity. Angular momentum is moment of inertia times angular velocity. Again, I'm not really going to get into any math with this one today. But because linear momentum can be conserved in any situation, so can angular momentum. So, of course, any conservation law says that total is constant, right? So that means the total angular momentum of the system remains constant as long as there's no external torques acting on the system. In other words, nothing extra twisting going on. Now, this is sort of a classic example of what a spinning ice skater can do, or how a helicopter works in terms of that particular idea. If you ever look at the design of a helicopter, this can be a beautiful helicopter right now. The helicopter has two rotating blades. It has the large one that does most of the work of lifting it, and then it has this one on the tail. Well, the reason it has that is because the tail rotor is because of conservation of angular momentum. You see, as this thing rotates, the big blades start to rotate. Well, while it's sitting on the ground applies a counter torque to prevent the helicopter from moving. When the helicopter lifts up off the ground, because there is an angular momentum due to angular velocity this way, and the symbol for angular momentum, by the way, is capital L. So since there's some angular momentum here, it would create, to conserve angular momentum, momentum going the other way. In other words, an angular velocity the other way. In other words, the body of the helicopter would start whipping around the opposite direction of the propellers. So what this propeller at the back does is it provides an external torque to prevent that swinging motion of the helicopter itself. Now the other example, of course, is an ice skater. If you've ever watched an ice skater go into a spin, you don't see them constantly applying forces by kicking their leg on the floor. In fact, what they do is they go and they kick their leg out in the air. And what happens is then they slowly bring their body inward. And for an ice skater, going from sort of this look where your leg and arms are way out while you're spinning, you have a very large radius here. Okay? And so you have a certain amount of angular velocity at which you spin. Now, when you suddenly crunch everything in, what you've done is reduced your radius. So if your radius goes down, your resistance to rotation, your moment of inertia goes down. And to conserve angular momentum, your angular velocity has to go up. And that allows them to spin faster and faster, simply by pulling their arms and legs closer. Now when they want to stop, they spread everything back out really quickly, and that causes their radius to go up, their moment of inertia goes up, and their angular velocity goes down, and they stop spinning. And that's basically the idea. So that whole skater thing works because you must conserve angular momentum. Let's look at the same idea of conservation of angular momentum in terms of a simulation. So here what we've got is our solid disk, mass of 0.1 kilograms, radius of 4 meters. And we're going to cause it to spin with an angular velocity of 4 radians per second. So we have a moment of inertia of 0.8 and an angular momentum of 3.2 kilogram meters squared per second. Now, let's change something about the platform. Let's say I double the mass. Well, notice doubling the mass doubled the moment of inertia, which immediately cut its angular velocity in half, but the angular momentum remained constant. Okay, conservation of angular momentum. Now, sort of the idea with talk about the ice skater. The ice skater changed her radius in the spin. So let's say this is our ice skater spinning here at 4 radians per second. And we're going to cut her radius down.
Whoa.
The ladybug said, whoa. Now notice by cutting the radius by 1/4, my moment of inertia went way down, actually by 1/16. And my angular velocity increased 16 times, spinning much faster. But again, I conserve angular momentum. And that's basically how that ice skater is able to spin faster and faster, simply by reducing her radius. Allows her to increase her angular velocity. And that's basically the idea of conservation of angular momentum. So that's sort of a quick idea, some other concepts around rotational mechanics. See you next time.